Thanks a lot for the kind introduction and also for having me here and giving me the opportunity to speak, despite the fact that I work not for Xanadu. And as just mentioned right now, I'm going to talk about quantum gradients. So let's start right away. This slide is basically about giving you a context for the whole model that at least I was having in the back of my mind when I prepared this full presentation. So we've now already heard about quantum machine learning, but we can never repeat the basic ideas too often. So the idea of quantum machine learning is to combine concepts from machine learning and quantum computing, and thereby basically offer a new toolbox to tackle some problems. Now, we are currently at the moment where we already have some first quantum computers, which means that we can already try out how quantum algorithms behave in practice on an actual machine. But we are still limited in terms of what the hardware can do. So we need to make sure that our circuits are short. We need to take into account that we have limited connectivity on the devices and that we have shorter coherence times. And all of this setting brings together that basically the main focus of currently implemented quantum algorithms are based on parameterized quantum circuits, where now we want to find a good set of parameters for those quantum circuits, which actually suffice a certain loss function or a certain condition, so to say. Now, this approach of quantum machine learning algorithms can be extended or can be used in a variety of applications already. This ranges from classification of data to generative learning to approximate some data loading, so to approximately load classical data into a quantum state. And we can also use it to implement some heuristics for optimization. And the list actually goes on and on. So what are now the basic building blocks for this concept of QML algorithms? Well, as mentioned, we have a parameterized quantum circuit, which acts as our ansatz. We have a cost function, which here in this setting that you see is an expectation value. Now, this expectation value is given with respect to an Hermitian observable, a Hamiltonian. And this Hamiltonian now encodes our problem. Now, what we want to do is to find a good set of parameters to find at the minimum point of our given cost function. Now, this optimization routine can have different phases, so to say. So either we can use some stochastic optimizers, we can make use of finite difference approaches, so some optimizers that use numerical approximations to gradients, or we can use an optimizer that uses analytic gradients. And those analytic gradients is the key point of this whole talk now. Now, let's extend this idea a bit and really understand what we're looking at. So imagine you have a cost function and a potential set of parameters which could fit in there. Now, this parameterized cost function can basically be seen as a landscape of hills where you want to find those parameters that correspond to the bottom of those hills. Now, we start at a random point, making a random initialization choice, so we end up at some point in this whole landscape. What we now want to do is to find the fastest path to the bottom. How can we know where the fastest path actually is? In principle, we would have to model the full landscape and then analyze it. But that's not very efficient. It's quite costly, in fact. So what we can do instead is to choose the direction of steepest descent, make a step, choose the direction of steepest descent again, and so on and so forth, and thereby continuously go downwards the hill. Now, I would like to point out the two elements or the two libraries within Qiskit that help you to integrate a QML algorithm in a smooth way. So the first one is the circuit library. The circuit library holds a class of quantum circuits which you can easily call and stack together and then apply for your algorithm. For example, you can use it to load your data into a quantum state. Here, there are some feature maps given where you pass in your classical data into the feature map, then this will generate a circuit, and then you can stack together this feature map, for example, with a parameterized ansatz, and then you can train again the parameters of this ansatz. Of course, there are also other circuits, such as those that apply arithmetic operations. There are some generalized gates in there, and much more. But I will stop talking about it for now, because if I would go on, then my 30 minutes would be over. And for further information, I would like to refer you to the documentation of the circuit library. The second part is the gradient framework. This was quite recently added to Qiskit, and I'm very happy that it's there now. The gradient framework basically takes an objective function in terms of an observable, respectively a cost function, which relies on the measurement outcomes of a quantum state and enables you to compute either something that is of a gradient type, a Hessian type, or a metric type. The whole framework is built in such a way that it's modular. You can easily add new elements and combine them also with some sub-elements. Now, to make this a bit more clear, within the gradient base, we now have two different types of gradient classes, the gradients and the quantum natural gradients. For the Hessians right now, we have a Hessian matrix, and for the metrics, we have the quantum Fisher information. Now, for all those classes, we can compute the gradient type with respect to the circuit parameters. Now, to compute the gradient with respect to circuit parameters, this can be done in different ways. And this is then what we call a circuit gradient method. So the circuit gradient methods that are currently implemented are, first of all, the parameter shift. Then we have a linear combination method in there and a finite difference approach where you perturb your parameters with a small epsilon and then recombine the results. For the parameter shift and linear combination, I will not say too much right now because we will learn more about them a bit later on. So for the quantum Fisher information, we may also compute this on a circuit level by making use of different approaches. And the current implementations support also a linear combination approach, which uses an additional working qubit and computes the full QFI. Then there are also two approximate methods in there, namely one that computes a block diagonal approximation, just making use of some commutation relations, and the same approach just for getting a diagonal approximation for the QFI. And with this, I'll now, for the remainder of this talk, going to discuss why gradients. So why can an analytic direction be helpful? How can gradients help us to understand the problem geometry at all? Then how can we integrate those circuit gradients, and what do I mean with parameter shift and linear combination? And the same for the quantum Fisher information. So let's start with why gradients and why can an analytic direction be helpful. So for the plot on the right, what you see is a noisy simulation where we use the noise model for the IBM-Q Montreal 27 qubit backend, where we used 1,000 shots for each point evaluation. Now, the underlying state is given by a hardware efficient parameterized ansatz for 9 qubits, and what's important to mention is we did not do any additional circuit optimization now for this noise model, but just took the circuit as is. And the Hamiltonian is a very simple one. So we have 2 CCs on the first 2 qubits and an X on the second qubit. The task at hand is we want to find the minimum eigenstate for this given Hamiltonian. And now we can compare the evolution of the loss function for different optimizers for, let's say, what we see here, 200 iterations. So the blue line that you see here is SPSA, so simultaneous perturbation stochastic approximation, which is a computationally quite efficient optimizer. And the perturbation that was chosen here is set to e to the minus 2. Then the violet line is given by gradient descent method that employs analytic gradients. And the third method is a gradient descent that uses a finite difference approach to gradients, where the perturbation is also being set to the e to the minus 2. Now, what is interesting here is that the analytic gradients still seem to work fine, but the noise in the system seems to give the other 2 approximate methods a bit of a trouble. Now, I should still mention here that if we play around with the hyperparameters, so change the perturbation, or for example, do multiple runs and average over those approximate methods, then we could still get better and improve the whole technique. But I think what is very interesting here to see is that analytic gradient descent seems to be more robust than the approximated optimizers in this noisy setting. Now, why gradients? So we've already seen in the picture before that gradients help us to find the steepest descent. So to say this more generally, they help us to understand the slopes of the loss landscape. And now combining those first order gradients with second order gradients helps us to not only understand the slopes, but also the curvature. So we understand how fast slopes go down and where it bends, where it's up and down, basically. And then we can also use the quantum Fisher information matrix to get a better understanding of the geometry underlying our quantum state. So taking all of this together already helps us to get an idea of the whole problem setting, of the whole training space, and whether the optimization can even achieve a good solution, or whether our setting is basically a bad choice. Good. Now we're ready to talk about gradients. The example that or the gradient types that I consider here are gradients of what can be written as an expectation value with respect to a Hermitian observable. Now, we assume for simplicity that our state is prepared. I'll draw something. So that our state is prepared here by a single unitary u theta. Now, this unitary can be written as the exponential with respect to a Hermitian m. Now, this Hermitian m, again, can be written as a sum of parameterized coefficients and Pauli operators. What this tells us now is that we can write the gradient of our state according to this function. So basically, we just need to take the gradient for our m and then multiply this onto our state. This is very nice, and now will help us to find help us to understand how we can compute the circuit gradients. In the examples on the following slides, we will even choose a simpler case. So instead of having an arbitrary unitary, we have a state that is prepared by a single Pauli rotation, where our Pauli matrix is here, this sigma. Good. Okay, so the first gradient type that I'd like to talk about are parameter shifts. So suppose your unitary, which prepares your state, has 2 distinct eigenvalues plus minus r. Now, what we can do is compute this expectation value once when we shift our parameters by plus pi, and then this factor divided by 4r, and once by minus this factor. And then we can simply just add them up together and get our gradient. This is very nice and neat. We don't have to add additional qubits, but just need to evaluate the same circuit structure with different parameters twice, and then just add them up, given some factors, and get our gradient. Now, here we see the example for those polyrotations, which is a very common type of quantum gate. And in this case, we just take those plus pi half and minus pi half shifts, add them up, and get the gradient. Now, I will not do the maths here, but please feel free to verify this at home. You just need to use these formulas, and you can easily see that the above holds. Now, what if we have a unitary that doesn't suffice this criteria? So maybe we don't have two distinct eigenvalues of plus minus r. We now have two possibilities. Either we decompose our unitary into a set of gates which then again suffice this property, or we search for a decomposition of the derivative of our unitary in terms of coefficients alpha k and other unitaries ak. Now we can make use of let's say a trick. We rewrite our gradient as 2 times the real part of this expression. Now let's have a look again at the gradient for our trial state, and we see that the gradient for this is given by this coefficient minus I half and the Pauli matrix. Now we plug this into our real part up here, and we get this formula. Okay, so we're set, and we can make use of the circuit structure down here. Excuse me, please, the noise. Okay, now we can make use of this very cool circuit structure. So we have our state, and we use an additional working qubit where we can now use intercepting controlled gates and then measure this qubit and get our gradient. How this looks in this example is the following. So we use a controlled gate for our Pauli, and then since this is a Hermitian observable, we can measure it here. We measure our qubit on top, and we get our value. Now, of course, we can also do this for higher order gradients. For the parameter shift, we only need to basically shift twice. So this is what you see here. If we evaluate the gradient for the second order, then we shift the observables twice by this term and add things up again and get our gradient. For this linear combination approach, there is this very beautiful circuit, which was in this Quantum Generative Adversarial Networks paper, and I love it. So here we take 2 working qubits and use these 2 qubits to apply intercepting controlled gates, and then finally evaluate again here the top qubit and measure the Hermitian observable down here, and we get our gradient again. Good. For the quantum Fisher information, we can do some quite similar approaches to evaluate it. So the quantum Fisher information looks as you see up here. So basically we have the real part of, we could say, the inner product of a gradient vector. And then on the right-hand side, this is what is often called the phase fix, in particular in the context of variational time evolution. And now we suppose we have a simple state that is generated by 2 Pauli rotations. And again, our gradients are as we've seen it before. Okay, now we can again either use a parameter shift approach or a linear combination approach. For the parameter shift, I'll show you how to compute the full QFI. For the linear combination approach, I will now only consider the first term. The second term can be done similarly, but just for the sake of time, I will stick to this one. Okay, so for the parameter shift, again, you see here that the parameters are shifted. What I would like to draw your attention to is that we here compute an overlap between these two states. This means that we may need to implement that we may need to double the circuit length or add additional registers to conduct some swap test-like approach. But this helps us to compute with those 4 terms the full QFI. For the linear combination approach, we can see again that this is written as the real part of a gradient expression. Now, in the circuits before, we've already seen that this helps us to compute the real part of a particular expression. And to integrate, again, this expression, we evaluate our state gradients and plug the respective unitaries into the circuit in a controlled manner. Now, just to mention this, so the quantum Fisher information is a very, very nice thing, which can help us to construct the quantum natural gradient. So the quantum natural gradient is basically a gradient that is, so to say, rescaled with the quantum Fisher information. And what this means is that we can construct a gradient object which takes into account your problem geometry. So the classical counterpart, so natural gradient, has been used a lot already in machine learning and been found to be quite useful. So it would be a hope in the quantum context that we can also make similar discoveries. Okay, so to wrap up my talk, I would like to raise some points which are important to think about in the context of quantum gradients. So you may have heard of what is called Barren plateaus. A parametrized quantum circuit can often exhibit 2 design characteristics. What this basically means is that gradients will, in this case, vanish exponentially in the number of qubits. So there's quite a lot of research going on for barren plateaus to find out in what situations they arise, how can we prevent them, what is the allowed scaling of a circuit length to avoid this problem. So to wrap this statement up is even if we can compute the gradients, we need to make sure that they're not zero and that they can actually help us to train our model. The second point is noise. So the example before was supposed to be a motivation to show you that analytic gradients can help you to train given noise. But there's still a large-scale study needed to investigate the effects of noise on analytic gradients and also to draw a comparison to gradient-free optimization methods. So as mentioned before, gradient-free optimization methods, if we tune the hyperparameters, can work better than what I showed. And most of the times, this brings me to the third column, the complexity for those methods is smaller than for the gradients itself. So we also need to evaluate this. What's then really the complexity? How does it increase? And eventually also, what's the trade-off between this additional complexity, those additional measurements and evaluations that we have to do, and what does it bring us in terms of performance? So with that, I would actually like to thank you for your attention and take any questions.
Thank you. Thank you so much, Christa. That was fantastic. So before we get into specific questions from the chat, I'd love to kind of follow up on that last slide and say, of these different areas, what is most interesting to you? What are you interested in kind of looking at?
Definitely noise these days. So I think it's really, really cool that we can already run our experiments on the quantum hardware and test the effects in real life. So a noise model is still a noise model, and on a physical device, there are so many effects which are very, very hard to track with a computational model. So yes, exactly. I would definitely say to better understand the effects of noise and on gradients, and then also in combination with different optimization schemes.
Okay, cool. I've got a couple questions from the chat about a couple of specific slides. There's one I was interested in as well. So can you go back to the slide where you were showing us the different gradient descent methods or types, the comparison between the three?
Sure. There was.
Perfect. So yeah, so we have Definition Forge asks us, what does loss mean in this context?
Oh, the loss was, I believe, the value of the eigenvalue in the sense, but it might be that there's a normalization on top. I'd have to check. I'm sorry.
Okay, no problem. I think same slide, and I was wondering this too. You've got the 0.3 there in the Hamiltonian. What's the 0.3 sneaking in there?
Oh, I was afraid of that question. Unfortunately, I was really
No.
just trying out some random example. I was playing around. I actually wanted to include an X term that was important to me because those off-diagonal parts in a Hamiltonian can change the situation quite a lot. And the 0.3 was, I'm very sorry, basically a random choice.
That's a great answer. I mean, I don't take any shame in that. I make random choices all the time. If it works, it works. I like it. That's fantastic. Another maybe more general question from Taste the Painbow with 2 W's is asking for, and this is not meant in any kind of challenging way, just why would someone maybe use Penny Lane over Qiskit or vice versa? Really, how do the two fit together or complement each other or contrast? Anything you'd like to say there?
That's definitely a good question. I don't know if it's a hard question. So I'm very impressed by Penny Lane, how well they've integrated all of those QML applications. I would say Qiskit has those different application areas, so acts on very different levels, and we still need to integrate more on the QML side, and we can definitely also learn a lot from Penny Lane how they already approach this. And that's also something on track. So now that we have our gradient framework in there, Qiskit will also further work on the integration of QML applications.
Right. Yeah, I think that's a great point. Like that introduction of the gradient framework is a big one. That must have been a ton of work. Were you heavily involved in the gradient framework stuff? I imagine.
Yes.
Yeah.
Yes, exactly. I work together with 3 colleagues.
Oh wow! Any particular challenges or stumbling blocks you ran into working on that?
I think here the design was a very important point that we also talked about a lot. So right now we have, in particular, the circuit gradient methods or those different metrics where we did see that there are basically like different puzzle pieces that we could fit together in different ways. But the question was, how do we make this in a modular way to allow like the user to write their own circuit gradient method and still use all the high-level logic that is integrated in this full gradient class? And what happens if somebody finds a new high-level gradient class but still would like to use those circuit gradients? So fitting the puzzle pieces together in a modular and reusable way was definitely a key part here.
Well, yeah, sounds challenging. We might have to have you back sometime for a hands-on with the gradient framework. A more sort of like general question. I'm like on a personal level, I like I mentioned with Maria coming from South Africa. You're joining us from Zurich right now. Could you tell us a little bit what it's like living in Zurich? What's the winter like? How's the skiing?
Yeah, that is actually the point. It's awesome for skiing. It's very, very great. So I'm very happy to live here in Switzerland. I'm originally from Austria, and also there we have lots of mountains. And in the winter, I couldn't imagine being far away from the mountains. Just, I don't know, jumping on a train, taking my skis, and going on the slopes. It's awesome. It's great.
Okay, so mountains over beach for you then.
Yes, I would say that. Although I did try to surf, but I failed quite badly.
Oh no, surfing seems extremely difficult. I've never tried myself, but I can only imagine. Um, so I'd like to hear a little bit about your, and actually, I think hopefully the chat would as well, about your sort of like your academic journey. I mean, you know, you're a pre-doctoral researcher with IBM. This is an amazing achievement. What did you go through to get here?
Um, so definitely okay. This is, I'd say, a tough question. So I guess I already started in school. I always liked physics. I always liked computational science. Um, and then it was a path through studying physics and then also taking internships on the side to more and more understand what I liked a lot. And after some time, it was very clear to me that on the one hand, I love quantum mechanics. On the other hand, I love computers, I love coding, I love integrating some software. So for me here, the part to go into quantum computing was quite clear. And then I was very happy to find a position with IBM where I now have the possibility to do my PhD together in a collaboration with IBM. And also ETH, so one of the universities here in Zurich, and thereby basically already in my doctoral studies learn and do what I love, namely actual integration of quantum machine learning algorithms.
Okay, wow, that sounds great. I understand that you got interested in quantum from a very early age. Is that right?
Yes, that is very true. So that's a bit of a funny story. So I was on the car with my parents when I was quite little, and it took so long, and I was a bit annoyed, and I was like, "When are we there yet?" Um, and then I really wanted to invent a teleportation device, and I told my dad, and then when I was, I'd say, a teenager, he gave me a book about quantum teleportation, and of course, it didn't help me to actually invent a teleportation device, but it got me interested about quantum even more, and it actually led me to the path to study physics. And for me, this was a very important point. I mean, it was just something very small from my dad to give me this book, but small things can actually steer the direction of your career and your life.
Yeah, wow, that's a great story. Do you happen to remember the book?
Yeah, I do. It's from Anton Zeilinger.
Okay, that's
Yeah.
cool. That's a great story. Yeah, I totally get it. On the same topic of uh, let's say materials to get us going in these fields, we've got Samuel Lives is asking, what are some recommended research papers for gradient-based and gradient-free methods in quantum computing?
Oh wow. Gradient-based and gradient-free methods. Okay, that's a difficult question. I could give a couple of very nice references on gradients, and that also includes actually a couple of authors from Xanadu. So for a comparison of gradient-free versus gradient-based optimizers, um, I'm trying to think, but I can't think of any. I can recommend you to check out the optimizers that are within Qiskit, and then also have a look at the optimization itself. But I'm not familiar with the paper right now. I'm very sorry.
Okay, no problem. We can always gather that later and we can put it into the
Yeah.
chat or post it somewhere. All right, let's see what else is coming in from the chat. So we've got, oh, interesting. Okay, so somebody this is Niranjan saying he's currently using natural gradient descent, but needs a better one. Any other optimizers available?
Have you tried to use natural gradient descent with some advanced gradient-based optimizer schemes? So using, I don't know, some BFGSB schemes, and then using natural gradient instead of the gradient, basically?
Okay, so that would be some suggestions to try
Mm.
to improve that. Looking forward to hearing what Niranjan says when they try that out. So we're going to try something here. We're going to play a little game. So my understanding is that Christa, you're not familiar with a game called Mad Libs, is that right?
Yes, yes. Unfortunately, like, yeah, my first question when I heard this name was like, what's that?
That's great. That's perfect. That's exactly what you want in a game like this. So I'm gonna prompt you with some questions. I'm gonna need some answers. Feel free to be as silly as you like for this. This is not a serious game by any means. So what I need from you is I need a 4-letter acronym. Imaginary, real, just a 4-letter acronym.
Oh my God. Okay. 4-letter.
There are no wrong answers.
Okay. I need to count I need to count the letters. I don't know. Okay. Ball.
Oh, okay, okay. B-A-L-L. Let's call it ball. And okay, next, an adjective that ends in ly. So for yeah, like
Lovely.
lovely. I like that. That's a great one. That is a lovely, lovely choice. Lovely. Okay. Next, I'm going to need so 2 things: the name of the last name specifically of a scientist from the 1900s, and the last name of a scientist from the 2000s.
Oh my God, my history knowledge is so bad. Okay, I will definitely make a fool of myself with that one.
That's the
Okay.
point. Don't worry.
Oh my God. Okay. What year was Schrödinger in?
1900s, I think, is
Okay.
acceptable.
Okay.
Yeah. So
Okay.
we'll go
Let's
Schrodinger.
go with
Okay.
for the 1900s. Okay, and then for 2000s, yeah, I'll go with Anton Zeilinger.
Okay. Okay. Seilinger. All right. Okay. We're getting there. So now I need something that is used by a construction worker.
A shovel.
A shovel. That's great. See, you're catching on quick. The responses are coming faster. This is great. Don't overthink it. That's always the thing. Okay, so how about a sign that you would see in a shop?
A sign that I would see in a shop, like sale.
Sure, sale. Sale's great. Okay, couple more to go. So next, the name of a cocktail or a drink.
Um, a Manhattan.
Well,
Oh
Manhattan.
no, can I change that? Can I
You
change
can
that?
change it. I'll allow it this time. Okay.
Okay, thanks. I'll go for gin tonic.
Gin and tonic. Okay.
Yeah.
That's a good one. One of my favorites. Okay, we're almost done. Just 3 left. I need a fictional place.
A fictional place. Okay. Oh, 1 second. Okay, I have been watching Star Wars quite a lot lately, so I should remember any of those planets' names. But I can't. Oh my God. Okay, I need to think of something else. Oh, okay, I have it. Hogwarts.
Hogwarts. I love it. Perfect. Got Hogwarts. We need a cute animal. Actually, the plural of a cute animal, but we'll just
Penguins.
penguins. Yes, I agree. And finally, a pair of rhyming words. So 2 words that rhyme.
I don't know. Fair flare.
Fair flare. All right. Okay. So the way that Mad Libs works is typically, in my day anyway, we would have a paper copy where you'd have these suggestions. You'd have to put them in, and then you'd expose the solution, which is a sentence where you filled in certain words, and of course, it ends up sounding a little bit maybe not as intended because of these interesting words. So we can read this out now. So what we've got is the following statement from Christa. As we enter the ball era of quantum computing, quantum machine learning is becoming lovely important. New ideas such as the Schrodinger-Seilinger algorithm, the variational quantum shovel, or the Sale theorem are revolutionizing the way we think about quantum systems. This progress has even inspired several new software libraries, such as Gin and Tonic from the University of Hogwarts, and Penguins, developed by the startup company Fairflare. So that was Mad Libs.
Oh, I love it. It's very nice.
Yeah, those are some great, excellent choices. That was a lot of fun. I'm glad you enjoyed that. I enjoyed it as well. I hope the chat enjoyed it. Yes, the chat enjoyed it. I have confirmation. Wonderful. So finally, I'd like to give you a chance. I know that you're very passionate about open source software, and this is something that IBM is passionate about as well. Maybe give you a chance here to explain what is it about open source software that
Yeah.
that excites you, or that why do you feel so strongly about open source software?
Definitely, definitely. So right now, I mean, I've mentioned it a couple of times, but we're in this position where we not only know about quantum algorithms, but we can actually get them run and make them happen and use them. And the one important thing also to interact with the computers now and to make this happen is the software. And developing software is not easy. It's now a completely new paradigm. We're in quantum mechanics. It's a new computational setting. And there's so much knowledge out there that we can basically use all together to push the quantum research to a new level. So if we can support the software side and if we can push the software side, then this will also help us to gain better insights in research, and to better understand our results. But to make this happen, we need to work together. So if people all close everything up, if all the code is basically hidden, then everybody has to work on their own code by themselves. If we have it open source and give people access to it and to work together and to get ideas, also from other codes, to integrate them into your library, then this helps us to push this whole science to the next level, basically, and to advance things all together. Yes, exactly. And even more so, we're now at a stage where this is a global world and we can interact so easily. I mean, this is now a full hackathon happening online, basically. And open sourcing even further helps us to collaborate on a whole new level now. We can be people in completely different locations, just having access to this GitHub repo, and then integrating your ideas, combining it with the ideas of somebody else, and then basically work together on a whole new level.
Couldn't agree more. Like, that's fantastic. Maybe just to play devil's advocate for a second, though, there must be some downsides to open source, or some potential pitfalls that need to be navigated when you're open sourcing something.
Of course. Okay, this is of course a good point. Okay, maybe say twofold. So you still, as a company, usually you still want to protect your IP in some sense. But then again, here you can also make a trade-off. So of course, if you want to publish a paper, then you wouldn't put your code online right away, but first you would keep it to yourself, get through your research, and then put it online. And yes, exactly. Basically, take the trade-off here, because what do you want to publish first, and what should be accessible for the broad audience right away, and then on the other hand, of course, open source also requires us to maintain more organization, because also if different people work together, then everybody has a different logic in their hand. They build up things in a different way. And here it is also important to make sure that you have a structure that fits together. And this is definitely also overhead in work, but an important one to be able to put those puzzle pieces together and to get it working.
Okay, yeah, nicely said. Do you see, are we making the right progress towards this sort of open source future? Is there more that we can be doing to push this forward?
There's always more that we can be doing, but at least from what I hear now from many researchers is that they're pro open source and that they absolutely support the idea. And also quite many of the companies, including IBM, but also many others, they also now have this mindset that we want to open source software and that we want to work together.
Yeah, that's fantastic. I'd like to see that future as well, everything open source. Christa, this has been fantastic chatting with you. Thank you so much for the talk and for spending some time with us today, all the way from Zurich. Really appreciate it. Thank you so much. Thanks everybody as well in the in the Twitch stream watching. We're going to be back in about 15 minutes with the last talk of this section. So stay tuned. We'll be right back. Thanks again, Christa.